Study of the effect of different dopants on optical properties of ZnS thin films. Abstract pure ZnS thin films and doped with different dopants were prepared onto glass substrates by chemical bath deposition method. ZnS films were deposited using ZnCl2 as zinc ion source, Sc, NH2, 2 as a sulfide ion source and ammonia hydroxide, NH4OH, to controlled pH value. The solution temperature is 70 C°. The transmission measurements were carried out in the wavelength range, 300–2000 nm using Jasco V-570 Double Beam, Spectrophotometer. The optical energy gap of prepared films were determined. It is 3.8 eV for pure ZnS thin film. It was found that the energy band gap values of films doped with copper and antimony are greater than pure films, while its value for doping with silver is less than pure films. Photoluminescence properties of prepared films were studied. The photoluminescence spectra of the pure films are showed 3 peaks centered around 325,450 and 505 nm. The ZnS Cu films had 1 peak at 323 nm. The ZnS Ag films also had 3 peaks centered around 329,440,460 nm. While the ZnS Sb films, 1 peak is observed at 318 nm. It was found blue shift for peaks centered around 325 nm when ZnS thin films were doped with copper and antimony, whereas a red shift in it for doping with silver. Keyword: zinc sulfide, pure, doping. 1. Introduction. Zinc sulfide, ZnS, is one of the 2,6 semiconductor materials. ZnS thin films with wide band gap, 3.73 eV, which crystallizes in both cubic and hexagonal forms, have recently received intensive attention to be used in many applications. It has relatively high refractive index and high transmittance in the visible range. ZnS compound is a promoting candidate for a large variety of applications including photonic crystal sensors, optical filters, light-emitting diodes, anti-reflection coatings, flat panel displays, phosphors, and photovoltaic cells. ZnS is also an important phosphor host lattice material used in electroluminescent devices, ELD, 1,2. Moreover, the content elements ZnS are non-toxic to the human body and are very cheap and abundant, 1,2,3. Previously, ZnS thin film have been deposited by many different techniques: thermal evaporation, self-assembly technique, spray pyrolysis, electron beam evaporation, photochemical deposition, PCD, closed-space sublimation, pulsed laser deposition, molecular beam epitaxy and chemical bath deposition too. Among the various methods, chemical bath deposition, CBD, is the most commonly used because of its simplicity, low cost, and coating large area of the semiconductor with good quality and high purity of deposited thin films. So, it was used in the present study to prepare ZnS thin films. The main goal of this present work is to study the influence of different dopants, Cu, Ag, Sb, on optical properties of ZnS thin films too. 2. Experimental. ZnS thin films were deposited on glass substrates by chemical bath deposition technique. The cleaning of substrate plays an important role in deposition of thin film by CBD process. The substrates were cleaned with a soapy solution, rinsed with distilled water and then with nitric acid followed by isopropanol, kept in an ultrasonic bath and finally rinsed with deionized water and dried in the air. ZnS films were deposited chemically using 1M zinc chloride ZnCl2 as zinc ion source, 1M thiourea Sc, NH2, 2 as a sulfide ion source and ammonia hydroxide, NH4OH, to controlled pH value. The total volume of the chemical bath was 100 ml. These solutions were mixed together in a separate beaker. Afterwards the mixed solution was stirred for 15 minutes. The pH value was maintained 11.6. When the deposition temperature reached 70 ± 1 degree C, pre-cleaned glass slides were introduced vertically inside the substrate holder, dipped into the solution and left for deposition for 180 minutes. After completion of film deposition, the samples were removed from the beaker and allowed to cool. The deposited films were then rinsed with deionized water to remove soluble impurities and dried in air. Schematic diagram for the deposition is shown in Fig. 1. Figure 1. Schematic diagram of chemical bath deposition method. The chemical reaction occurs as follows: 4,5,6. 2 equals 2 plus O. NH2 equals 2 plus SH plus O. S2 plus H2O. ZnCl2 Zn plus 2 plus 2Cl. Then the formation ZnS is according to equation Zn plus 2 plus S2. ZnS, 1. The ZnS film thickness is given by 7 equals, where is the difference in mass before and after deposition, is the bulk density, and is the area of the film. The optical measurements, which included transmission and absorption spectra in the wavelength range 300–2000 nm, were carried out using Jasco V-570 Double Beam Spectrophotometer. 3 results and discussion. Optical properties. For more investigation, absorption coefficient A, cm1, of the ZnS thin films was determined from the transmittance measurements using Swainpol's method 8,9 equals 2.303, 2. The nature of the transition, direct or indirect, was obtained by using the relation 10, 11, 12, 13, H equals H. 3, where A is constant, A is absorption coefficient and Eg is the bandgap energy. For direct transition the N value is 1/2, whereas for indirect transition the N value is 2. Bandgaps were obtained by plotting HV against OV 2 and extrapolating the linear part. By extrapolating the linear portions of the plots of OV 2 versus HV to where OV 2 equals 0, the value where the extrapolated line cuts energy, HV, axis is the bandgap. The OV 2 versus HV plot of pure and doped ZnS thin films with different dopants, Cu, Ag, Sb, are shown in Fig. 3. The optical bandgap value obtained from this plot is presented in Table 1. It is 3.8 eV for pure ZnS thin film. This value of the optical energy gap is in good agreement with previously reported value. The optical bandgap, e.g., value of doped ZnS thin films with Cu, Ag, Sb, dopants are presented in Table 1. Impurity pure Cu, Ag, Sb. 3.8, 3.85, 3.78, 3.9. It was found that the values of optical energy gap of the ZnS thin films doped with copper and antimony are greater than pure films, while its value for doping with silver is less than pure films. The increase in the bandgap of Cu-doped ZnS film can be related to the structural modification of ZnS thin film. It can also be supposed that the copper ions can replace either substitution or interstitial the zinc ions in the ZnS lattice, creating the structural deformation. On the other hand, the increase in the bandgap or blue shift can be explained by the Burstein-Moss effect 14. The Burstein-Moss effect results from the Pauli exclusion principle, and is seen in semiconductors as a shift with increasing doping of the bandgap, defined as the separation in energy between the top of the valence band and the unoccupied energy states in the conduction band. The shift arises because the Fermi energy, F, lies in the conduction band for heavy N-type doping, or in the valence band for P-type doping, 14. While decreasing in the bandgap of Ag-doped ZnS can be attributed to the influence of near band levels. A small fraction of the Ag incorporated into ZnS lattice act as an acceptors and create localized levels near the valence band 20. The increase in the bandgap of ZnS after Sb doping can be explained by the Burstein-Moss effect. Photoluminescence properties. The photoluminescence spectroscopy provides information about the structure, bandgap, impurity levels, and localized defects in semiconductors thin film. So the room temperature photoluminescence spectra are recorded for pure and doped ZnS thin films in the spectral range of 300–650 nm. The PL spectra are shown in Fig 3. The photoluminescence spectra, PL, of the pure ZnS films showed 3 peaks centered around 325,450 and 505 nm. It is well known that the luminescent peak centered at 325 nm could be assigned to the UV excitonic emission. The ZnS thin film reported previously have photoluminescence emission with bands in the range 450-505 nm associated with sulfur vacancy-related donor and valence band 15,16,21. One peak at 323 nm was observed for ZnS Cu thin film related to the optical energy gap, 3.85 eV. It means that the Cu dopant made blue band shifts towards the short-wave part of spectrum 22. Also, 3 peaks centered around 329,440,460 nm were observed for ZnS Ag in Fig.3. The peak at 329 nm corresponded to the energy band gap, 3.78 eV, while photoluminescence emission with bands in the range 440-460 nm is associated with sulfur vacancy 18,17,19. ZnS SB thin film showed one peak at 318 nm. It is assigned that the one peak is due to band gap of ZnS SB thin film. It is noticed that the optical energy gap may be increase when it doped with copper and antimony but decrease with silver doping. Figure 3. Photoluminescence spectra of pure and doped ZnS thin films. Conclusion. Pure ZnS thin films and doped with different dopants were prepared on glass substrates by chemical bath deposition method. The optical properties of these films were studied in range of 300-2000 nm. It was found that the optical energy of the ZnS thin films doped with copper and antimony are greater than pure films, while its value for doping with silver is less than pure films. From photoluminescence spectra of pure and doped ZnS thin films were studied. It is clear that the photoluminescence spectra, PL, of the pure ZnS films showed 3 peaks centered around 325,450 and 505 nm. It was found blue shift for peaks centered around 325 nm when ZnS thin films were doped with copper and antimony, whereas a red shift in it for doping with silver.